Hello, let's solve minimum cost pathways teleportations. I would assume you have read the problem statement. And once you read this type of problem, usually the first idea is to use some kind of Dijkstra on an augmented graph. And before writing anything, we should realize that this won't work, right? Because there are m times n nodes. And unfortunately, for each of those nodes, you would have two neighbors from the normal moves, but you would potentially have m times n other nodes from the teleportations. So you would have at least 2 plus big O of m times n neighbors. On top of that, we would do augmentation. So that would mean that instead of considering the graph of size m times n, we would probably consider the graph of size m times n times k, because we want to differentiate when we arrive at node ij if it's been with 2 teleportations or 6 teleportations, right? That shouldn't be the same state. So there's an additional times k in here. And so we would have already something like m times n times m times n, maybe times k, right? And that's not even accounting for the log factor. And if we look at the constraints, m and n of 80, so that would be something like 80 to the power of 4, k is 10, so even if we ignore this is, I think, 4 times 10 to the power of 7. So even if we ignore the log factor, even if we ignore k, we already have 4 times 10 to the power of 7 operations, right? And we probably want to keep that under 10 to the power of 7 or even under 10 to the power of 6 typically. So that's kind of why Dijkstra won't work in this problem. Well, it will work, it'll just be either time limit exceeded or memory limit exceeded. And so the way to solve this is going to be dynamic programming. I unfortunately don't have any intuition why this is the way to think about this problem. Nothing satisfying apart from, well, we can't use Dijkstra. Maybe we could try and use dynamic programming with a clever way to define our states. So if we go, I'll give you a very rough overview of what we can do, and then we'll code it, and then we can analyze the complexity. But if we do something like dp ij and the number of teleportation corresponding to the minimum cost to get to ij by using at most n teleportations. Then we hope that we can end up at a complexity that is less than the horrible m times n times m times n times k that we had earlier. Right, so first of all, the size of this dp, which will be a list of integers, is m times n times k, so that's perfectly fine. If we think about the initialization, the easy kind of thing is to think about dp ij0, right? If we aren't allowed any teleportations, then this problem is a very, very standard problem where you can only move right or down. So it's a graph, every node has 2 neighbors, and there's even a nice topological order in that graph. So it's very easy to solve, right? It will be something like the minimum. So to arrive at ij, you either come from I minus 1, or you come from j minus 1. And then you have to add grade ij because the cost is the value of the destination cell, right? So either you come from either you just moved down or you moved right. move right, move down. Obviously we have to be careful. If I is 0, then we can't be moving down, but that's very standard. So that will be the initialization. Nothing fancy, nothing horrible in terms of complexity. Now for the transitions, well, those were transitions already, but for the general transitions where we consider TP, IJ, and teleport, we have to be sort of clever, right? If we are naive about it, we can just say this is the minimum over, well, those two are still valid, except we're doing something like this. And we can add this. But there's now a sort of a third option, which is because we are allowed to use n teleport, we can teleport from somewhere, and we can teleport from a state in which n teleport will be n teleport minus 1. I guess that makes sense. So we can teleport from anywhere as long as we're satisfying this, right? So it will be the minimum, and you'll see that if we do that, then it won't work. But it's still good to show it. We would have dp I previous, j previous, and teleport minus 1, plus 0, because the cost of this move is 0. For all I previous and j previous, such that grid I previous, j previous is bigger or equal than grid of I, j. Right, the destination has to be the small one. And here the destination is ij, and where it comes from is ip and jp, which here is x and y. Oh, sorry, ing. So here ing is x and y because this is the destination, and ip, jp in my notes is I, j in the statement. A bit confusing, but yeah. All right, so that should make sense. The unfortunate thing is that we have again our m times n times k, but this minimum is also bigger of m times n. So we have to be clever about this minimum. All right, that's the whole sort of challenge here. So to compute this, we have to be clever, otherwise TA. And the way to do that is to use two lists. We will use a first list that I can call, and it will make sense after I explain why, min cost from cell of value v of size max of grid plus 1. And so what does this do? This will just represent the minimum cost, I should put v, minimum cost from all the dp, I, j, and teleport minus 1, such that grades I, j equals v. So among all the cells that have exactly this value v, we want a minimum cost. And the reason why we don't really care about what those indices I and j are is because we just, here, we don't care about where IP and JP were. We just cared about their value of the DP, and we cared about the fact that their value was bigger than the value of the cell we were on. Okay, hopefully that makes sense. So two things. This can be computed in big of max grid plus m times n, right? So you have to spend max grid energy to create a list of size max grid, obviously. And to fill this here, you just do very basic loop for I in range, for j in range. So this is m times n. Unfortunately, we don't. So this will be nice. This list here would be useful if we wanted to compute a minimum for all IP JP such that the grid is equal here. It's not equal, it's bigger or equal. So we have to use a second list, and we will also use min cost from cell above value v. And you may wonder, why am I even bothering doing this if what we actually needed this is because to build this we need this. So this is also a list int of size max grid plus 1, and it's really the same. The only difference is that it will be the minimum cost from all the dp ij and teleport minus 1 such that the grid was bigger or equal than v. So it's the min cost from cell, I guess cells above value v, right? Cells. Hopefully that makes more sense. This can be computed in big O of max grid. And the reason why is you can just do min this equals the minimum of the value above, because we're looking at all cells above value v. So all cells above value, I guess v, is cells above value v plus 1 are also valid. And surprise, we'll use that list. So it's either bigger or equal than v plus 1 or v, which is exactly what that says. Right. And so this can be computed in O of max grid. So this is okay, and now we can have this in big O of 1, because hopefully you can understand that this is just min cost from cells above value v at index grade ij, right? Because instead of this v, you have grade ij. So instead of this v, you also have grade ij. And that's pretty much it. That's a lot, but there's nothing more to this problem, right? You just need to come up with those states and those sort of clever ways to avoid the calculation of this many a times. And the intuition is, if you compute the minimum for all IP JP such that this is bigger than 9, and then you have to compute it against for all the values that are bigger than 8, well, you're doing duplicate work, right? Because above 8 and above 9, they both include to iterate over the values 10, 11, 12, 13, 14, all the way to 10 to the power 4. So you should realize that here you're doing duplicate work, so you can do some sort of pre-processing here to not have this duplicate work, right? All right, let's code this. What is this? All right. The first thing to do is initialize our DP list. So that's very easy. We said it was 3-dimensional, so that will be the last dimension is k plus 1, because we want the number of teleportations to be 0, 1, 2, 3, all the way to k, so that's k plus 1 values. This is the m dimension, and this is, what am I doing? What am I doing? Yeah, sorry. So yeah, so let's put infinity here, and then we have this here, and then we have this here. And so that should be because we're looking at a minimum cost, we put infinity everywhere initially, and then, and only then, we will fill this up. So initialization is kind of a simple one-dimensional DP problem. So we said this, so we'll do something like for I in range, length of grid, for j in range, length of grid 0. We have this, but we obviously have to initialize dp 0, 0, 0, 0, right? If you start from the beginning and you want to arrive at the beginning, it will cost you 0. And the only problem is if I is 0, this will be invalid, so we have to say if I different 0, else 10 to the power of infinity. What happened? Sorry, and the same here. Right. If we leave it like this, the problem is that the first iteration here will be when I is 0 and j is 0. Sorry. And so we set 0, 0 to 0, but because I is 0 and j is 0, this will be 10 to the power of 18. This will also be 10 to the power of 18. So we'll put it back. We'll put back 10 to the power of 18, which is obviously wrong. So we have to do something like this. Basically, if both are non-null, so if one is non-null or the other one is non-zero, then we do the update. Otherwise, there's nothing to update. We already dealt with it here. And so that's the first step, right? The second step, we said that we wanted to do this, but to do this, we needed to compute this, and to compute this, we needed to create those two lists. So let's create those lists. And the thing I mentioned is those lists, maybe I didn't mention, but those lists are only valid for the states where there's n teleport minus 1. Right? When you consider the state with 8 teleportations, then you can sort of quote unquote come from the states with 7 teleportations. Right? You don't really care about the states with 6 teleportations. So that's why this only considers n teleport minus 1. The problem is when you create those lists, you want to have the max of the grid and you're not going to compute it over and over and over again. So let's just compute it once and for all. Max grids, put it 0 for I in range, length of grid, for j in range, length of grid 0, max grid equals max between max grid and grid ij. There are about 1 billion ways to do this, so you can just use comprehensions if you want. Now, for n teleport in range 1 to k plus 1, right, because we've done 0 already and we want to stop at k included, and this is excluded. And obviously, I didn't say it, but at the end we return dp minus 1, k, right? We want to arrive at the bottom right corner, and we are allowed to use k teleportations. So we said that was a list of size max grid. We also said that we wanted to create this list of the same dimension. And to fill up the first list, we said that we would just iterate all over all the I, j, and teleport minus 1, right? For I in range, length of grid, for j in range, length of grid 0, missed cost from cells of value v. So here the value is the cell where we're at, equals the minimum between what we already had, because maybe there's another cell with other coordinates that had a lower cost, and the cost we have here. Then this is sort of like a suffix thing if you've done prefix sum exercises. It's very similar, except it's suffix in a suffix manner. So we'll do something like for v in range max grid all the way back to -1. We'll say something like this is the minimum between, and I said it earlier, the thing above and v. Right, so we can just copy this. And I think that's correct. Right, that's what I said. Yes, that's what I said. The only problem here is if v equals max grade, this will call max grade plus 1, which will be out of range. Wait, 1 second. First of all, I made a mistake because those are size max grid plus 1, because you want to be able to be at index max grid. So you need to have size max grid plus 1. And if I come back, we still have a problem because when v is max grid, this calls max grid plus 1, but if you have length max grid plus 1, the higher you can call is max grid. The highest index you can call is max grid. So first index, when v equals max grid, you obviously don't care about max grid plus 1, so you can just set it as max grid equals, well, above max grid is the only possibility is to be exactly at max grid. Hopefully that makes sense. If that makes sense, then we're done. All right, there's probably typos in there, but I'll correct them later if there are some. And so now we just compute this, except this is free. Right, so if we copy this, obviously for I in range length of grid, for j in range length of grid of 0, dpij and teleport is the minimum if we move down, if we move right. Obviously we have to be careful. If I diff from 0, else 10 to the power of 18. If j different than 0, else 10 to the power of 18. And then this is just min cost, right? This is literally the min cost from cells above value this. So min cost from cells above value v, and v here is grid ij plus 0 because the cost of teleportation is 0. Cool, let's just run some test cases. Amazing, it works. I would have bet I made a mistake, but I didn't. Let's submit. And this passes, right? And so for the complexity, creating DP is m times n times k. The transitions, because this is big O of 1, the cost is also m times n times k because it's basically big O of 1. Actually, that's 3 operations, but that's big O of 1. To compute this thing, we spent big O of max grid plus m times n, and here we used max grid. So overall, the cost is something along the lines of max grid plus m times n times k, right? Because this is irrelevant because this is bigger. And the space complexity, I believe, is the same because this is m times n times k, and this is max grid. So space and time complexity. Cool.